So I thought I didn't do the recording yet because I didn't have time. Yeah, so what I'm gonna do is do today and then finish the nano composite this afternoon, post it up. So you'll have to, if you want to see it, you'll have to look at it. And then Friday there's a homework. It's like a repeat homework from last year. So because I didn't have time to kind of look for homework. So, but it's an extensive homework. You know, so it's a good homework to do. So kind of reviews the subject too. So with the two, hopefully we'll have enough. Then next week I'm still thinking, so we got like 3 weeks left, right? Like this, including this week, or 2 weeks or something. So we got time to do membranes and do artificial intelligence, machine learning. That's what I think we have. Did anyone know offhand? Or? This is homework 11. We can do homework 14. So we got, I guess we got 3 more homeworks we can do. Is that right? Or let's see, it's March and then we end on the 21st, right? So we have 3 more weeks. Yeah. Yeah. So we can easily do membranes, artificial intelligence, and one other thing. Unknown origins. If anybody wants anything other than membranes, we can do that. You know? Or I can come up with something. So this is already recording, the screen share, and the video is okay. Right, so everything should be all right. So I'm going to go through this homework. So the one group got 103, and then the one group got like 70. So it was pretty broad range here in this thing. Anyway, so I think I kind of went through this. Let's see, explain how the broad range usually obtained. Okay, so he does something different because, so the time temperature superposition is for polymers, right? But when you start adding nanoparticles, they don't have time temperatures. So you can't exactly do that, especially if you get to high loadings of nanoparticles. Like in a tire, it's going to be like 40% carbon black. So they still use time temperature there, but it's a cheat, right? They're cheating when they do it. So he decides not to cheat. So he goes to do creep measurements. And then he uses the Schwarzschild method, whatever, to shift the creep measurement into the, which is like looks like it's an empirical power series. Even though there's a analytic theory to do it using this relaxation function, which he gets. So he could have gone that route to get it, but he didn't. I mean, I think the Schwarzschild method kind of does that, but it does it. It looks like it's a power series, right? When you look at it. Some reason I got like a cough. Then I touched the mouse, and the next guy's going to get whatever I got. Yeah, this is a Maxwell that you should be familiar with. And then I don't know what Schwarzschild does. He ends up with this, looks like an empirical function. It's just a power series to get something. I don't know. So basically he transforms that to get the broad range, which is different. I've never seen that done before. But the Schwarzschild paper has a lot of citations, so I think it's probably something people are doing. Just don't kind of know about it. Did I say how many citations? Schwarzschild method. I don't say here, but anyway, so that's the thing. So people didn't get that he didn't use time temperature superposition. Everyone figured out what time temperatures, but if someone asks you time temperature superposition, then the first thing, how you should answer it isn't the way he answered it. No. You should first say, I'd like you to be able to do this. Like first say Arrhenius, you know, so because that's simple, like the WLF, you're not going to be able to understand what it is, right? I mean, not offhand. So to say like the viscosity is some other viscosity, and then it's going to be like some energy. Oh, sorry. Oh, it's not clear. All right. That can be fixed theoretically. Wow. It looks like it's zoomed in too, right? So how does that happen, you know? Like that isn't something that it would, plus is the wrong direction. It's making a lot of noises. Ooh. That thing's got quite a magnification, huh? Yeah. Right. So anyway, so you got this thing. So this thing you should have in your brain, like that should be permanently bonded in your brain. And it can be in that form, or it can be in this form. Right? Energy of activation. So you got the ratio of some energy to the thermal energy. And that's going to be deciding something. Something's going to happen. It's thermally activated. That's the WLF. So if we say, how does this thing work? That's the equation. So for 90% of the time, you can just use that equation. Like if you take PDMS, just PDMS silicone rubber and put it into a viscometer and measure the viscosity at different temperatures, this thing perfectly fits it. No problem at all. So you need just one parameter, this energy of activation. If you go like close to the glass transition, then you get problems because the T isn't right. So you have to add a Vogel temperature, right? That allows you, that absolute zero isn't going to be the zero temperature. This temperature has to be in Kelvin, by the way. Like it doesn't work with centigrade. We'll find out it doesn't work. And then the other thing you can do is say that's an energy. Well, energy has like delta H minus T delta S. So energy has a temperature in it too, you know? So if you're talking about the temperature dependence of viscosity, well, there could be organization happening as the fluid goes through temperature things, whatever. So it could be some entropy. So you probably want to put a temperature. And then you have one parameter, you have 1, 2, like 3 parameters. WLF calls those C1, C2, C3. Or you call it enthalpy, entropy, and Vogel temperature, which is a much better way to talk about it because those things have meanings and C1, C2, C3 don't have any meaning. Okay, so it's basically that's time temperature position. So this viscosity you could put in frequency 0 would be some temperature kind of corresponding to TV. So this ratio becomes the shift factor AT. So it's ln of the shift factor is going to go with 1 over T and constant over T, right? Negative. So, and then you can convert a viscosity at some temperature to a viscosity at another temperature with 3 parameters, or 1 parameter if it's a simple system. So water, anything, it's just going to be Arrhenius. So Arrhenius was a Swedish guy from like 1890, I think right? 1880 something, 1887, I think. He said that because of the CO2 being produced by burning coal, there's going to be atmospheric warming in like 1887. And it was well accepted at that time. Like he published that, he had calculations, he showed the Earth was going to warm. Right. So we've known about that like 130 years. Right. And, I mean, it's basically like been known. Anyway, so that was, Arrhenius is known for the equation, but he kind of did that too. Like if you Google, you can find out whatever the actual date was, but anyway, so if you asked about WLF or time temperature, that's what how you should answer it. You should first start with the simplest thing, which is that Arrhenius function. Also the other thing, this is also called the Eyring rate theory. So if you talk about like the activation energy for chemical reaction, that's going to be the concentrations of the reactants, the ratio of the products of the reactants, and that's going to be an exponential. And the idea is the reaction is thermally activated. It's the same idea. So Eyring was a guy at Cornell, and he was like in the 1950s, I think. So much later than Arrhenius, but he uses the same function. And then people take the Eyring rate theory and apply it to like everything, like herds migrating in Africa through the Serengeti are temperature dependent. And they use the Eyring rate theory to talk about the rate of the transfer of the animals through some kind of whatever savanna thing. Really done. In fact, all right, so the guy worked with knew Eyring, you know, and Eyring was at a meeting, I guess as the story goes. And some guy's talking about the animals migrating and using his rate theory. And we say, and Irene was in the audience in the front row. And he goes like, yeah, we're using the Irene rate theory to talk about these gazelles. And then Irene got up and started asking him questions about how a gazelle is like a chemical reaction. Like basically the guy didn't know that he was talking to Irene, even though he was using Irene's equation. So he got in trouble doing that. But anyway, so that's the way it goes. You have to be careful what you say. Let's see. So achieved using creep measurements, and then the things. This is like his whole point of the paper is these shoulders on this plot, right? So the shoulders on the plot show this thing about the shape factor. So the fact that it has this kick out here is a shape factor. Then this little nib thing. So when he says the terminal viscosity, terminal area, right? So that means terminal means flow. In rheology, terminal means that you reach the flow regime, because that's the simple regime. So terminal means the end of the line, which means it's just going to be a Newtonian fluid, like water. That's a terminal fluid. Okay, so terminal doesn't mean to the right here, it means to the left. So one group was talking about something over here, or the rubbery plateau or something, but he's talking about this little, this is the terminal region, because you have power 2 and power 1. Right, for the modulus is power 1, this is power 2, that's a Newtonian fluid, right? So basically in this region, everyone's happy because they know exactly what that is. That's just like the viscosity is the slope of that, of the G double prime thing. So then you reach a rubbery plateau, and then other things happen over here, right? So basically those two things are the things that he's interested in, is trying to understand. In this little nib thing is where he gets his packing, the whatever Magnanus, whatever effect, the packing effect thing, this Maragoni effect, the wine glass thing. Anyway, so the shoulder, that's what those shoulders are. And then it changes with concentration. The first one changes, this knee part changes because that has to do with the curvature of the particles. And as the particles get bigger, they get less curvature. So curvature of particles is ranked by 1 over the radius, right? So you talk about the 1 over the radius is this curvature factor. So you can have like K1 and K2 is going to be proportional to like the surface energy of a system. That's 1 over R1. So if you have something like this, you have like R1 and R2. So you have 2 curvatures usually. They can be equal, and then the energy is going to be proportional to this K thing, 1 over the R's. So in other words, the more you fold the surface, the higher the energy that you get out of it. Right. So anyway, this knee has, and if the particles change size, then that knee is going to change. Right. So the concentration changes the particle size, and then the droplet size, and then the droplet size changes the curvature, and that changes the energy of that thing there. That's more or less how I see it. But the subtle increment has to do with that's where because it's so subtle, then you can start making things up, right? I mean, that modeling that subtle difference, well, you can do it with this complicated equation, wherever that is, that giant equation. Or you can just, so basically you can say anything you want about that thing because it's such a subtle effect. I mean, so if you believe, like, this equation. So this complicated equation, you can pick out the deep. So the reason to use this complicated equation is because it's not following Maxwell behavior. It's got that kick out, and it also has that little thing that comes out. Those are the sources. So you have parameters. You always want to say, like, where did that parameter come? Why do you need that parameter? So where did it come from in the raw data plot? If you can't answer that, then the parameter is kind of meaningless. So you can't see a kick out, and that's going to give rise to why you need two extra parameters in this complicated equation to deal with it. You better know, like, why you need that equation. So anyway, that's what this thing is about. Then equation 3 gives a generalized Pagliari model that tries both, blah, blah, blah. Why is it not present? All right, so I mean that no one really got that, so basically, so why is this happening is because they're spheres, so the spheres can approach, and there's some region that isn't close approach when you have a spherical particle, right? So this thing, when it's spheres, then they have a point of contact. That point of contact, everything has to get out because you're squishing it there. If you have sheets, there isn't any point of contact, right? So this whole thing about, so the answer should have said something about spheres, that a sheet isn't spheres, so you aren't going to get this contact point and you won't have this effect of squishing out the things. The squishing out the things on the surface is what causes a concentration gradient, and that causes the Margione effect, which is to drive the fluid back in to dilute it or something, right? So the concentration gradient drives motion of the fluid or the solvent. Anyway, so that's what that thing's about. No one really answered that one. Then the Coco plot. So one group said the Coco plot had to do with the relaxation function, or the relaxation function had to do. So these two things look the same, but they're different. So the Coco is just G double prime versus G prime, and this thing is an integral. It's like finding the base spectrum for the thing, but they both will end up with that you have peaks that in each peak has to do with one relaxation time. So they both show that feature, but kind of for different reasons, I guess. One is just this Debye relaxer function that should be a circle. And the other one, it's actually the spectrum of relaxation, which has peaks at certain relaxation times. Right. So the more peaks, the more relaxation times in the relaxation spectrum. And the more circles, the more relaxation time in the Coco. So they sound like they're the same thing, you know, actually, I mean, but basically they're different. You know, so one group couldn't work out that difference, I think, but I think that's an important difference, you know, but basically the consequence of not knowing that, I'm not sure what it is, but explain how the relaxation spectrum are related to storage and loss. Why is relaxation spectrum easier to understand? So because it's easier to understand because you can see the I mean, that's why he shows it, you know, he shows it. So no one actually answered that very well. Like why is this plot better than that plot? You know, well, this plot, all the features of these little nuances, right? Some nuance like a knee and some nuance like a little kick out. In this plot, all the features are like well seen like peaks. So you can really pick out the relaxation and you can understand what's going on here. Like this is the number of things relaxing at that time, right? So this is actually the number at that time. This is the modulus, like what, I mean, could be anything. So you have to use a model, like a Maxwell model, to figure out what these curves are. This is direct interpretation, like you directly see what the spectrum of relaxation is. This is the bell. A bell is a straight up and down line on this. It's got one frequency. Right. And then this thing, like what would a bell look like here? Well, it's going to be like a Maxwell model. So it's going to be a gradual, it's got one relaxation time that, you know, and the Coco will be a single circle. So anyway, these are easier to understand. And then also you can easily see like when something weird happens, like you get this network forming. So this last one is a network formation. And then the idea that G prime follows a power law and G double prime will follow the same power law, that means you have a network. So if you start seeing the moduli following a power law, just log plot, it's a straight line. It's not 1 and 2 for Newtonian fluid, then that means you have a network. That's the Winter model for network. So he sees that when he has this network kind of structure, he sees a network with a large, so the low frequencies are large sizes. So large sizes, he sees a network. That's the signature there, and that's the signature here for the spectrum. So anyway, this is a lot in this paper, I think, but it'd be good. I mean, one group got kind of everything, and everyone else kind of didn't. I mean, I got some of it, but so, and then compared to bulk samples, so the multi-layer, because it doesn't have curvature, that's the answer. Basically, you don't get the Marigoni effect, and it's a simpler system with the when you just have layers. So anyway, so that everyone did kind of okay on it, I guess, but basically one group did really well on that this homework. I think they had 2 grad students too. So all right, so that's that business. Any questions or anything on that stuff or on that paper? hopefully it was okay. I mean, it's like everything's like a little bit involved. So I'm not expecting, like if you get this on a qualifier question, I'm not expecting you to be able to be like a genius, but I'm expecting you to be able to fend for yourself when something is thrown at you. So just use what you might be completely wrong, right? I mean, you might answer something and just be totally off track, but demonstrate that you can put up a fight, you know, like demonstrate you can pick out some parts, and I know some things. And I'm going to take the tools that I know and try to take this thing apart. It's like Arrhenius, like saying this is the Arrhenius behavior, like time temperature. That's really simple, and like it'll apply to anything. Anything is thermally activated. So basically that would be like a place to begin with any kind of look at any kind of dynamics, right? So it should be like reaching your toolkit, and you can just put those things in. Anyway, so we get this nanoparticle stuff. Let's see. Let me hide this. Oh, yeah. Nanoparticle stuff. Nanocomposites here. All right. So modify this a little bit. I found some papers and then I realized they're already in it, you know. So I think this is pretty comprehensive. And also the thing is, this field seems to be dwindling down. Like most of the papers are going to be like 2017, 2018, 2019. And then like you don't see a lot of papers on nanocomposites now, you know. And there's so these are all review papers from 17, 18, 19. And a lot of the work was 2006, 2008. So I guess that's like 15 years ago now, right? So basically this seems to be a field that's reached its peak and is kind of dropping, I think, in some ways, even though it looked like it was going to just keep growing at some point. So it's like I don't know, maybe the electric truck business seems to be doing that. Lordstown. You know why the electric truck business is crashing out? I have no idea. In fact, I bought some of their stocks and I'm really disappointed. It's like built in Cincinnati, you know. I think because there's a lot of, at the beginning in the science, there's a lot of BS going in. All right, first off, science is just like rock and roll. Like you're going to have like fads, reggae, punk, whatever, hip hop, whatever. And it's going to go through and everyone's going to run over and do hip hop, you know. And then like there's going to be a lot of money in it. So more people come in, oh, there's money there. I like hip hop, boom, boom, boom. And then all of a sudden it's like, what is this crap? It's terrible, you know, it's like go somewhere else. So anyway, everything's like that in science. So there's some level of standardization of the thing. All right, so industry is what guides the standard level. You know? So like there is a need for nanoparticles in materials, you know. There isn't a need for necessarily for research in nanoparticles and materials, you know. So this is showing like Vaya's the head of AFRL in Dayton, you know, like he's the research lab. I think he's the head of it now. Wani, I went to school with her. She's at University of Pennsylvania, and she's kind of like the leader of nanoparticle or something. And then Sunat Kumar's at Columbia. He's like kind of the theoretical leader in nanoparticles. This is kind of a good group. 2017. There are a lot of seminars and things on this and meetings and stuff. And I just say like, there's all this stuff. These are the kind of particles you can make. So notice they don't mention like carbon black, which is like the original nanoparticle. So and the most popular nanoparticle and the most popular composite, which is tires, right? So and that was invented in 1940 or something, maybe before that, right? So anyway, so it's like rubber without nanoparticles has no tear strength, so it just rips apart. That's number one. So tear strength is the number one reason to put carbon black in tires, because the rubber is really tough once you put it in, right? It increases the modulus, which is good or bad. Like if you want to have grip, it's bad to increase the modulus. If you want to have wear, then it's good to increase the modulus. So it's a trade-off, and it's frequency dependent what happens to it. And then another big reason is that it's conductive. So like if you didn't have, so if you start, like if you go to your car door and you get a shock, that's because of silica in your tires. And if you didn't have, and so they put it in a blend, you can't put in pure silica. Silica has a lot of good things for It reduces energy consumption. So they're called green tires and you have a lot of silica in it. Like you can cut it in half, but basically you're going to develop electric charge as you go down the road at highway speeds and you'll arc. You can arc, So in the old days, before they had this done right, that you would have like a metal strip that went down to the road to drain off the static charge in your car. Yeah, and some people still have that. So I mean, like if you get a problem with this thing of grabbing the door and getting shocked, you can buy this on Amazon, like a little thing that drags on the ground. It just goes from the frame to the ground and gets rid of the charge. So
I think
it's dangerous because you get gasoline is incredibly dangerous. Okay, like I used to smoke, and I had this pickup truck and it smelled like gasoline, like it had some kind of leak somewhere. And I drove it for years like that and chain smoked at the same time. So it's kind of like I never really thought much about dying in a flaming ball of a pickup truck, but it can happen. So even they say like cell phones at the gas station, it says right on the pump, don't usually see people talking on it. It's like the fumes are flammable, and if that goes, like the whole place is going to go. But anyway, so what were you saying? Sorry.
No, I'm just talking about the charge.
Yeah, charge arresters. Yeah. Yeah. So they have that in Nigeria or something, or
yeah, even in South Africa.
Oh yeah.
Those charge arresters.
Yeah. Oh, you mean at the gas station?
Yeah.
Yeah. At the gas station, they have charge arresters. Yeah. Anyway, so that they don't mention that in this thing. Like these are like the star guys. They don't say like carbon because I don't know, it's dirty, I guess. Say like silica, titania. So silica, these are like large scale industrial produced materials, like the DuPont makes titania. I mean, they have a huge factory in New Jersey across from Wilmington. They don't. It's not DuPont anymore. It's maybe Chemours or something. Anyway, so and it can be used as a catalyst support, and it's used for white paint, and other things. And this is used for beer filtration. That's a popular use. And then basically it's in everything, desiccant. And then barium titanate. So these are a functional, like cadmium sulfide is for photovoltaics and stuff. Cadmium selenide. Those are kind of, cadmium's really deadly, but that makes a nice, it's got an absorption, the solar spectrum right at the right place. Iron's used for pigment. So it's a bunch of different things here. And then they throw in C60 for some reason. Then they say like, oh, how are you going to, so then from their perspective, they have spheres and they're going to put something on a surface to make it mix in well with the polymer. And then they're going to somehow get something out of that, right? So that's the idea. Like this is the stuff in the middle. So they actually, the whole thing is like a picture of what the thing is. So you have the particle in the middle, like an inorganic particle. Then you have some coupling agent on it. Then you're going to have some kind of reactions that you do, like raft is a simple chain growth polymerization method. There's thiols and azos and whatever different ways. I don't know what dyes are doing here, but these are like the reactions you use to couple between the matrix and the polymer. And then what's the nature of the surface is going to be like, I don't even know, this is like weird here, but basically you're going to have, whether you have like one chain length at the surface or multiple chain lengths, whether the chains are packed tightly, like the grafting density along the surface. So this is all like single particle. You have spherical particles of the stuff and you have to put stuff on the surface. In industry, you have like silica and silica coupling agents, silane coupling agents to use to mix with organics. See, silica doesn't, this polar, it's got hydroxyls on the surface. You put it in an organic polymer, it's not compatible. I mean, so you can couple onto that silanes. You have a condensation reaction. The end of the silane can be a alkene chain or something that'll mix with some polymer, right? Or you can actually graft a polymer onto silica, even commercial silica. I mean, how that's actually done. So you could take the silica manufacturers like PPG can like put stuff on the surface and sell you a bag of silica that's got surface treatment, or you can just, the tire companies basically dump the silica in and then put in silica coupling agent, just compound the rubber with no solvent. So what they get out, I mean, sometimes it works, sometimes it doesn't. So the understanding of it is minimal. right? So even the coupling agents or why you're doing it, it's not necessarily so clear cut, right? But there's a huge range of stuff that could be done potentially. They show some of it over here, like tires is the easiest one, then some kind of films and optical. So so this is a paper that was just published. I thought was kind of interesting because we were at one point we were thinking about having we put in to have an industrial center on flame retardancy here. And it turns out a bunch of people have done that, you know, so basically flame retardancy is kind of important, especially in aerospace where you, like the wires are all made with Teflon coating in airplanes to prevent fire propagation along the wire. So if that propagates in an airplane, everyone dies, right? So it's expensive to do. And then there's other ways to do flame retardancy. So you can, polyimides is a good one. So what polyimides do, they burn, okay, but they make char. So you end up, the char stifles the flame. So it burns, but basically it kills the flame the minute it starts. So it makes too much char. So things that produce a lot of char are good for flame retardancy. And then some things just don't burn, like silicon sealant or whatever. You can try burning it at home on your bathtub or whatever. It doesn't burn. So inorganic polymers. And there's other inorganic polymers they use. And then like Kapton and things. So polyimides are good for flame retardancy. And then any kind of this aromatic conjugated things are good. So Kapton and things are highly temperature stable because they have resonant structures, like the double bonds move around. So basically they're stable at high temperatures. So anybody who's doing liquid crystal stuff is happy to do flame retardancy too. So liquid crystal means you're going to have like high strength fibers, like bulletproof vests, like Kevlar vest. That thing's not going to burn. So you can kind of get two uses out of those things. One would be like flame retardant, heat stability, flame retardancy, and also bulletproof, super strong. And then you can add nanoparticles in to get it too. So what's the nanoparticle going to do? Well, it can form char. So you can put in a material that's going to form char, or you can put clays in. So exfoliated clays are really cheap. It's dirt, and they'll make kind of a char on the surface when you burn it. So clay is often used. It's like you're looking for something cheap that you can add. Silica and titanium are pretty cheap. They have good heat capacity, right? So you want something that could make a char, something that's got a high heat capacity, so it can absorb the heat. Without heat, you can't have fire. And then you also want to have something that can thermally conduct the heat away from the place where it's burning, right? So calcium carbonate, which is like rock, right? It's limestone. So you grind up limestone. So there's a company in Cincinnati, a Swiss company in Cincinnati that's doing this, that is like the leader in this field. One of my students works there. I can't remember the name. They're in Blue Ash. Their US headquarters in Blue Ash. But so calcium carbonate, turns out, is the main additive for polymers because it's really cheap. This rock, ground up rock, you know. So basically everything has calcium carbonate in it, and it's got a good heat capacity, so it can also be an effective flame retardant. So the question is, like, why do you need to go to like nanoparticles? So you can just put chunks of calcium carbonate in. So why would you want to go to nanoparticles in this thing? So I think that it's a good question, you know, because there isn't necessarily like microns. If you're below around a micron in size, you don't get much light scattering. So the thing, basically a micron is good enough. See, that's at the edge of nano. So if you go below a micron, you're kind of in nano, really colloidal. So basically, there's a good question, like why you would go to nanoparticles. It's going to take energy to make it. There's kind of two routes. You can go like bottom up and make the nanoparticles, or you can go top down and grind the things down. Grinding down is difficult to do. So calcium carbonate's completely made by grinding down, so it's hard to get it into nanoparticle. But it's still like probably the most used additive that you don't hear about. So anyway, so these kind of composites, and then you get to nanocomposites. So there's a lot of questions about why you're doing it with carbon black. With carbon black, it's going to be something. So this says, like, this is from that paper about flame retardant, ex situ and in situ. So you can, for instance, if you take PDMS rubber and the end groups are OH, then you can cross-link it with Look at all these things that they were selling this car, and I finally sold it, so but I still have the car sales things. Anyway, so you have this TIOS. So silica is like carbon, it's got four things, and you can put an ethoxy on the end. Or you can put a methoxy. So methoxy makes methanol that's toxic, so that's not good if you can avoid it. So ethoxy reacts slower, but so if you have PDMS, so it's like glass with a CH3s on it. Right? And you can make it hydroxyl terminated, it'll react with this and make ethanol. And then you get just SiO. So that'll be like a cross-linking agent for PDMS rubber, siloxane rubber. You can also do it by hydrosilation with a vinyl group at the end. So there's kind of two routes to do this. Anyway, so there's that thing. So if you put in extra of this TIOS, tetraethyl orthosilicate, then you can actually form silica particles in it. That's called in situ reinforcement. So this was done. UC was like a center for doing this, and then like Dow Corning, and then GE Silicons, which is now M something. Dow Corning is now Dow Silicones. Right. So GE is give the name Momentum. GE Silicones became Momentum. GE was once the biggest polymer company, and they kind of got Jack Welch and they got rid of it. So anyway, so you can do in situ. The biggest in situ is that process, like using TIOS to make silica, and then the ex situ is just dump the stuff in, milk compound it like a tire, or a solution cast something. So this usually that would be a specialty application, like cast a film with particles in it. Electrochemical is usually going to be polypyrrole or something. So that's kind of an odd one. I mean, that's a pretty odd one. They put it in there. So this is what happens. So in reality, like you're going to have, so this is 20 microns, like human hair. It's kind of like, this is a radius of a human hair. This is an X-ray tomograph. So you take a piece of tire, take it to a synchrotron, and then do a rotational radiography, and then from that reconstruct the 3D of the thing. You can do this in a TEM too, but this is, for this case, it's easier to do it with the X-rays. You can do it with neutrons too, but so that's the thing that's giving you your tear strength, whatever that is, like a network structure. That also gives you your conductivity. So basically all the properties you're looking for are coming from this thing, which is definitely micron size, but it's made up of little clusters of carbon black that have 3 levels to them. So the carbon black starting out, so the carbon black is starting out as little graphitic particles. You have little graphitic particles that are kind of like 5 nanometer in size, and they have basically a ball made up of graphite sheets. And this is just, you burn acetylene and you get the soot, right? So then those form, and then at some point the transport, I guess, is too slow, so they just start to aggregate into these aggregates between like 10 to like 200 of these particles. So there's like level 1, level 2 is that. Then those things cluster together to make level 3, and then those things make that network that you see. This thing is something like 0.1 micron maybe, and then this thing gets to like 2 micron, and this is hundreds of microns. Right, so you start out nanometer all the way to micron. You have like 1, 2, 3, 4 levels of the thing. It's complicated. It's not so simple. So it isn't like if you start here with a sphere, so kind of spherical, and say, I'm going to graft something onto that, well, that will prevent this aggregation from happening. And if the aggregation doesn't happen, then this agglomeration doesn't happen. If the agglomeration doesn't happen, then the thing you want won't happen. It's like making it more miscible is not going to do what you want it to do. So it wasn't by that process that they figured out. They just dumped the stuff in and it worked, right? So this is the kind of thing you want, you know, and this is kind of what they're doing. This is kind of what people are doing, right? So you take a monodispersed spherical particle of silica, which you can make by a solid gel synthesis using that same TEOS. You take that TEOS, put it into ethanol or into ethanol water mixture, then change the pH, and the TEOS will condense, produce water or ethanol, and then these perfect spherical particles will come out. That's called Stuber synthesis. It's been around since the 50s. So you can make perfect spherical balls. Or you can do that, you can do a latex polymerization of polystyrene. So you put polystyrene into water and you put some soap in and shake it up, and it'll make perfect little micelle blobs of styrene monomer. If you put in a small amount of initiator, those balls will like form perfect spheres. So you always get monodispersed polystyrene, PMMA, any of the free radical polymers you can get to be monodispersed spheres, right? So the silica is the most popular one because it's easy to do, like really easy to do. And you can also do it with sodium silicate, which is just sand that was like dumped into concentrated HCl, and you make this sodium silicate or dumped into NaOH. It's pH 14. So you dissolve the sand with NaOH, get sodium silicate, which is liquid. It's called water glass. It looks like water. And then you just raise the pH to 7 and it'll make these same Stuber spheres. And that's cheap. That's just whatever sand costs and whatever NaOH costs. And then you need some HCl to raise the pH. Anyway, so you can make those spheres, and they're going to have hydroxyls all over the surface. You can react the hydroxyls with some kind of coupling agent, like a silane coupling agent, and that can go, you can attach the polymer to that, right? So you can put as many of those as you want. That'll be like the density of graphene chains. So this is unitless, but it's basically how many per whatever cubic angstrom or nanometer. And then this is the ratio of the chain length. Like, is that, so you have this thing stuck in a polymer matrix as a polymer nanocomposite. How does the chain length of the thing on the surface match up with the chain length of the polymer that's stuck in? So, and presumably it's the same polymer. So 1 means they're matched, and then 0.1 means that you have short grafting on the thing, and then 10 means it's 10 times longer on the surface of this. So if it's 10 times longer, it's in this context of this thing becoming miscible, it's a bad situation, you get phase separation. If it's around 1, then it's good. Like you can get dispersed as long as you have a good density of these chains stuck to the surface. Right, and then weird things happen when you start dropping the graph density. So you get structures forming, like in other words, the beads themselves start to form sheets or strings. So the evidence for that comes from microscopy. I'll show you later. Like basically all the evidence for all of this comes from TEM micrographs, which, I mean, if you've ever done it or looked at them, like you can see a lot of different things in a TEM micrograph. Like you can see anything you want to see, right? So if you want to start talking about sheets and strings, I mean, there's always going to be sheets and strings in a TEM micrograph of nanoparticles. Right? Whether it's phase separated or well dispersed or whatever it is, right? So the TEM is a little bit subject to question whether that's valid or not. But this is kind of like the standard view of things, and there's been some attempts to formulate that into like mathematical formulas. There's also been significant effort because this is an easy thing to simulate. So you can there's a program called LAMPS that you can get for free, and basically it's just going to take computer time to run this, and you can make spheres and lamps, and you can make chains and lamps, and you can glue the chains to the spheres, and you can make the matrix of polymer. You can figure out a way to randomize it, then take the temperature and do something and let it cook, and then you can make, so people have made this phase diagram, quote unquote phase diagram, because it's not, these aren't phases, these are like topological organizations of things, right? I mean, dispersed and phase separated would be a phase if this was really phase separation, right? But what it is TEM micrographs, and you're deciding something here. So anyway, this line could be called a phase diagram, but the other lines, like changing into different topological structures, it's kind of like not a phase diagram. right? So anyway, so that's a picture of where things, you can see like Kumar, the guy at Columbia, and Winey, University of Pennsylvania. So those two people are like cranking out stuff in this, and a bunch of other people too. So then, I mean, that makes you wonder. So that could be like why the demise, like how important is this? Like if you can't, no one's really using this exactly in industry, like why is it even, why are you doing it? You know, so there's only, and also there's quite a range of things you can possibly do with spheres and sticking things onto them, but they've done almost all of them. Like say polydispersed chains, that's been done. Same polymer as the matrix, different polymer than matrix, different chain length, different bimodal chain length, different trimodal chain length, like all the different particle sizes. So at some point you run out of stuff to do. They've done it all. Basically in 10 years or 15 years, you've kind of run the gamut of it, I think, in a sense. Then you start looking at the dynamics of the chains, like the detailed dynamics of how the chain moves, which you've already seen is kind of a mess, right? If you're going to look at quasi-elastic neutron scattering chains at surfaces and try to pick up the different regions of the time relaxation of these chains and how it impacts the matrix chains and what the bound rubber. So if you just stick the particle into like you put carbon black into butadiene rubber, the surface is covered, the butadiene rubber kind of bonds to the surface more or less. It gets stuck there anyhow, some reason. I mean, for one thing, if the chain's random, right, and then it gets to an interface, we're going to have, because it's random, it can go in any direction, but it can't go into the particle. Then you got to get a density pile up at the surface because it has to. So you get a higher density of chains at the surface, and that's called bound rubber. You know, so basically you have kind of bound chains to any surface when you stick it into a polymer, right? So basically the particle size is going to be effectively larger than what you put in, because it's going to have this layer of crud on the surface, basically, whatever the plastic is it's stuck into. So anyway, so that also improves the compatibility with the matrix when it has the same polymer at the surface. Anyway, so if your object is this stuff, then you really have to kind of look at like the hierarchy of the thing, like what's going on with the hierarchy. So this is a scattering. So you take because the intensity is going to increase. We've looked at this already, but the intensity is going to increase with the concentration. So you reduce it by the concentration so they all overlap when you get to the surface. This is the surface scattering out here at the small size. So surfaces are the same. And you see like that this thing diminishes, meaning that these aggregates are like clustering, are overlapping each other. Like, oops, I don't have that here, but basically the aggregates overlap, that leads to this diminishment, and that reflects the speed of that diminishment with concentration, tells you how well the particles mix, right? And at the same time, at the large scale, this 2.2, these are the fractal dimensions, right? So this is a solid clusters at low concentration. At high concentration, 2.2 means you've reached like this thing. You've reached some kind of network forming in the thing. So it's a low dimension. It's got some random dimension of a network that forms. So in scattering, you can pick out the different kind of levels if you want to kind of simplify things, to think about it that way. It's possible to do it. Anyway, this is a guy. So we got a few minutes, but so anyway, I'm gonna take this and like finish up the things. We're on slide 9, and I think there's 50 slides, but I can do the rest pretty quickly. You know, so I'll put them on a thing. But anyway, so this guy McKay he was teaching in Australia. He's a nice guy. He's from Delaware. He was teaching in Australia, and then he came to the U.S. and started doing this stuff. And he was published some stuff in Nature on nanoparticle nanocomposites, right? So who else is on this paper? Tutich is a guy that does surface. He does like ice sticking to surfaces at Michigan. So he went to Michigan anyway. From Australia, he went to Michigan for some reason. Then he started doing this nanoparticle kind of grafted particle things. And he's the one that really came up with this thing that Sanat Kumar is showing here. This kind of mapping out of the anyway, he left Michigan and went back to he was at University of Delaware now. But so anyway, so there's this issue that the chain's larger than the particle, then it's dispersed. That's like this thing. So grafted versus matrix. So if the matrix is larger than the grafted, it phase separates. If the grafted is larger, so below 1 here, then it's dispersed. So McKay's the guy that figured that out by sticking polystyrene chains onto buckyballs, then putting them into polystyrene. And he also did it with dendritic polyethylene, which is like this thing. So basically, you can make a plastic. Well, we saw that in that last paper that their Janus particles are actually divinyl benzene cross-linked, like polystyrene or something, right? Or PMMA. So basically, you can make nanoparticles out of a single chain by cross-linking heavily to make the solid particles. He did that. He did that with dendritic polyethylene and polystyrene as some kind of dispersed particle. And then he just found, like, he got this mapping of how it goes with molecular weight, which basically is just going to tell you this thing, like this line between dispersed and phase separated. So that already existed back whenever McKay did that. That's 2006, and this mapping from Sanat Kumar is like 2013. It's like 7 years later, right? So anyway, things kind of go back and forth here. Then what else is in this? Then McKay actually did some kind of analysis. So we have the idea of putting a chain in, says n times chi, chi's per monomer unit, so n times chi gives you like the energy of insertion, enthalpic energy of insertion. And then he converted that for nanoparticles to be like, because only the surface of the nanoparticle matters. So the surface area with these chains times chi gives him this insertion enthalpy for the nanoparticle. Then he wrote an expression like a free energy expression that relates the concentration in nanoparticles to this enthalpy of interaction, and find out that that you figure out what the energy of a particle going into the matrix is, and then you can predict this kind of phase diagram from that using this kind of idea that when the energy of interaction is negative, it's going to be miscible. When it's positive, it's going to be immiscible. That's the idea. So you can get that with this kind of business. So then McKay came up with this model, which is like in all the review papers. Oh, we're out of time. It's 11:05. So I'll just start with this McKay thing, and then I'll record it and put it up this afternoon. All right. So anyway, so let me quit there, and then there's a paper up there for Friday that we can kind of go through. All right. Good. All right. Thanks. All right. See you later.
Hello, Prof. Hello, Prof.